classical method makes more sense. It's the one that most people are probably more familiar with. I've actually been using it when I talk about boys and girls and flipping coins and rolling die and things like that. But classical method, it's just going to be used if you have all equally likely outcomes. So like I said, drawing a card, flipping a coin, rolling a die, those outcomes are all equally likely. So if that's going to be the case, you're going to look at, find the probability. How many outcomes do you have altogether? And then how many outcomes do you have that are just in E, your event? So if you look, like I said, rolling a die, probability of getting an even number. You've got 6 numbers altogether. That's going to be your denominator. And of those 6 numbers, 3 of them are even, the 2, the 4, and the 6. So you've got 3 on top, 3 out of 6, which boils down to 1/2. So it's the classical method. So this is just another way of writing it, but it means the same exact thing. The number of elements in your sample space and the number of elements in E. That's just a different notation, but it means the same thing. Okay. So with this one, you've got a bag of M&Ms. They tell you how many of each color they have in each one, and then you're going to do, you're going to pull one candy out randomly. Okay, so in this case, our sample space is going to be all of the different candies. Our sample space isn't necessarily brown, yellow, red, orange, blue, and green. Because not all of those colors are equally as likely, but each M&M that you see in the bag is equally likely to be drawn. So that's why this one's going to be technically a classical method, because each M&M is equally likely to be drawn, not necessarily each color, because the color isn't a simple event, because here the event, drawing a brown candy, there's 9 candies that are in that event. So what we're going to do is figure out this probability. First, we got to figure out how many we have all together, because it doesn't tell us. We've got 9, 6, 7, 4, 2, and 2. So we get 30 candies all together. So we've got 30 little M&Ms in there. 30 M&Ms. That's going to be the number in my sample space. Sample space has 30 M&Ms. Each one is equally likely to be selected. So for part A, they ask me what's the probability that it's yellow. Well, I'm going to have a 30 on the bottom because that's how many I have all together. And then how many satisfy the event that the M&M is yellow? 6. So we'll do 6 out of 30, which is the same thing as 1/5. And I'm pretty sure they want you to change these to decimals in your homework, but I'm not for sure. Definitely at chapter 6 and beyond, it's always decimals. I don't know if they want you to do fractions or not. Okay, so for part B, what's the probability that it's blue? How many out of 30? 2. That's 1 out of 15, which is 0.2 divided by 3. That's 0.0667. And then the last one, oh, they say just comment on the likelihood. Okay, so this one's a little different. All right, so say what's the likelihood of the candy being yellow versus being blue? So this one is blue. Write that down. Blue. This one's yellow. So which one is more likely to happen? Yellow. So yellow has a higher probability. So yellow is how much more likely? Is it 3? Somebody said 3? Yeah. So yellow is going to be 3 times more likely than blue. And the reason for that is if you look, not at your decimals because that's kind of hard to tell, but if you look at the 2 out of 30 versus the 6 out of 30, there's 3 times as many yellow M&Ms as there are blue M&Ms. That's why it's 3 times more likely, because the probability here for blue, if you multiply it by 3, you get the probability for yellow. That's why this one's 3 times more likely. All right, so let's go back to the empirical approach. Okay, so sometimes you're going to have outcomes that are not equally as likely. So if you look at what's the probability that there's a wreck on the way to work in the morning, well, that's not always equally as likely every single day, or sorry, yeah, it's not something you can easily predict just by this. So what we're going to do instead is using the empirical approach instead of the theoretical approach. We're not going to look at how many things we have in the sample space. We're going to do experiments. We're going to base it off of how many times we've done this before. So what I would do with the empirical approach is I would say, how many times have I driven to work altogether? And then here, how many times out of those times did I see an accident? So I'd see an accident, 12 times out of 182 or something like that. But it's going to be based on an experiment. It's the same thing as the relative frequency. So probabilities and relative frequencies are going to be very closely related. So that's the formula we'll use for the empirical approach. Something that you really can't think about in your head to get what the probability should be. You have to base it on an experiment. Okay. So here they've got an example called Pass the Pigs. It's a game where instead of having like dice, they've got a pig, so something that's shaped a little funny. And then when you roll it, they've got all of these different outcomes that you could potentially get, but they're not equally as likely, not if you have like a nice cube die. So clearly these are not all the same because this one is a lot more likely than this one right here. So for this one, you have to do it based on an experiment. So they had a class with a whole lot of students. They rolled the pig this many times, and then we just kept track. So we get this nice little frequency distribution here. And then they ask us for probabilities based on that, and it's going to be the same kind of setup that we did before. We're just going to write out a fraction. So for 1A, they want us to do a probability model. I don't think we'll get through all of this before 9:15, so we'll just go ahead and stop there. We'll finish this one next time, and then we'll finish off with chapter 5 after Mardi Gras. Just be sure you do the homework and the quiz that's due tonight, and if you have time, go ahead and work on the chapter 4 project. Bless you.
Thank you.